is on Friday. 3.1.3.2, derivatives and differentiability. 3.3, rules for differentiation. 3.4, velocity rates of change and trig derivatives. And then the review. There we go. So let's see what exactly is going on. Because, man, if everything's moving that fast, wouldn't it be nice if we can get some homework done in class? Okay, so what are you guys supposed to be filling out for section 3.1 and 3.2? The slope of the tangent line is the derivative of the slope.
Tangent point is the
I'm gonna see
Oh dear. Okay, then wait. Wait, if we need to fill in this blank and we're all struggling, can you at least tell me what you did down here? Oh, derivatives are limits? Oh, use the groups. The slope of the tangent line is the limit of the slopes of the secant lines. So you knew the equation, but not the words that went along with it. As? True. So down here when you guys are doing the definition of derivative, for some of them, if you did start using h was representative of delta x. True? Okay. So let's say the limit as h approaches 0. What's one form of the definition of derivative? The difference quotient, right? Pre-cal already did that. Chapter 1a, they did the difference quotient. Did it well? Bless you, but they did it. Now the other two alternate forms, technically, they would be f prime of a, right? So f prime of x at a particular x equals a. So give me one of the other ones, and let's start off with delta x going to 0 again. What would that one be? Yeah, all we have to do is plug in x is equal to a, right? But that's not the only way. What's the other way? The limit as? Nice. And now we have, careful, minus difference of, right? Minus f of a all over. Because we need all of these to be 0 over 0 keep goings in order to have that impossible limit that we can still keep going and solve. I should say that impossible process of having the secant lines approach the tangent. Joe, what's up, bud?
If you did, instead of f of x plus h minus f of x on the top, if you did f of x minus h, would that still work?
In theory, you're just moving to the right instead of to the left. However, h is a delta x. And delta x's in my mind are like an absolute value. To which degree a minus would be irrelevant. Maybe I shouldn't say irrelevant. Why would you go minus a change instead of plus a change? My best answer to that would be delta x is representative of the change. A change could be to the left or to the right, and so in our notation, we want the positive or negative nature to be contained within the delta x and not indicated by a plus or minus. I'll leave it at that. In our general notation. So problem solving clues. Oh my goodness, it's a forever card. Right?
Yes.
At least some version of it. Is it the exact forever card? Maybe not the exact one. But it has information from the forever card. That could be helpful for the section. If it says to find the derivative at a point using the definition. Oh, wait a minute. Didn't we just do that? Oh, okay. Well, then we just need to go ahead and use the f prime of a forms. Does that make sense? So either the f of x minus f of a all over x minus a, or the f of a plus h minus f of x all over h. So use the f prime of a forms of the definition, alternate forms. Maybe I should keep it particular according to our forever cards. That's what we technically call them, right? The alternate forms of the definition of derivative. Find the tangent line. Tell me what I need to know. So you could say at x equals c. Is that okay? Y minus, which is found by, if they don't give me the y, I can find it by plugging into the function. So what would we write for the normal line? Wait, hold on. Normal comes from the Latin normalis. Normalis stands for perpendicular. So therefore, if it's normal, doesn't a perpendicular still go through the same point as the original? That's the one point they share. So therefore, what doesn't change? Yeah, the f of c or the... But what does change?
1 over, or negative.
You guys agree? Need the opposite and the reciprocal. Need the opposite and reciprocal. Normal, perpendicular. Ooh, here's the other snazzy word. Does anybody know the other snazzy word for perpendicular? Orthogonal. Orthogonality. So it could be perpendicular, could be normal, could be orthogonal. It all means the same thing. And the only thing that changes is the slope, and the slope changes, well, if the slope is found by the derivative, so it's the opposite reciprocal of the derivative. What's the one thing I need to continue to remind you all of? Not that you would ever make a mistake. But why am I going to circle in yellow this of C part? Does anybody know the common mistake I'm trying to have you guys avoid?
It's supposed to be a constant.
It's supposed to be a constant. It's a derivative at a value. It is an actual constant slope. Not the function has a constant slope. No. The function slope is always changing, right? But this slope in this line needs to be a constant, which is found by plugging in c to the derivative and getting out a constant. Every now and then some of you guys put the derivative function here with x's, and that becomes like a cubic polynomial, and I'm like, no, it's supposed to be a line. So no plugging in functions here. We want the function value at c, not just the broad general function. I think we only have one more page. Ooh, that's right. Section 3.1 was derivative, the definition of derivative, and 3.2 is differentiability. I was tutoring a kid, actually, I guess not in her class. She's tutoring kids at Moore Park in a business calculus class, and she was just getting a quick refresher from me on all the things that were on their first test. And their first test had limits in all their glory. Solving by hand, with graphs, with tables, with functions, 0 over 0, keep going, number over 0, nasty trig ones, etc. Limits, limit definition of the derivative, derivatives, higher order derivatives, exponential and logarithmic derivatives, tangent lines. What else do they have? Piecewise functions. Continuity and differentiability. That was their first test. It's a little rough. The teacher was nice and had skipped all word problems. There were supposed to be word problems on there too. But anyway. And as we were doing a quick refresh on the teacher's test review, which was very general and very vague, except for a few questions, differentiability was a big thing. Differentiability. And remember, if we're talking about differentiability at a point, non-differentiability at the point, there are multiple ways it could be true. First of all, a function might not be differentiable if the function isn't even continuous. If there's a discontinuity, automatically the function's derivative won't exist. So that's one thing. But then there are two other ways that the function might not be differentiable at a point. There are two different cases that could occur. I'm not so much as worried with you guys remembering vertical tangent lines and sharp points as you recognizing them when they come in examples. So I have some examples down below. Try to show you when you would have a vertical tangent versus a sharp point, when differentiability would fail. even though the function is continuous. This is a forever curve. We saw it last year. What I'm more worried about is whether or not you guys would identify not only that it's not differentiable, but how it's not differentiable. So vertical tangents versus sharp points, or I think our book calls them corner points. I think that's our book. I don't think it was last year. Or corner points. This function is not differentiable at x equals 0. But why? If the derivative is 1 over 2 root x, why or how is it not differentiable? Remember that the derivative is defined to be a limit, right? For a derivative defined to be a limit to exist, well, first of all, hold on, forget it. I don't even care about a limit. That doesn't exist at 0, right? But how does it not exist? F prime of 0, I could say equals, because it equals and then it doesn't exist. I could say 1 over 0. I'm not wrong. But what does this indicate? A vertical asymptote at x equals 0. And if the derivative has a vertical asymptote at x equals 0, that means the slopes are increasing either to positive infinity or decreasing to negative infinity as I come in towards that vertical asymptote, aka that tangent line, assuming that f was continuous. If f wasn't continuous, all bets are off. But assuming that f was continuous, we could integrate to find out what f was. It is continuous at 0. There must be a vertical tangent line that exists there because the derivative is infinite at 0. And what kind of slope does a vertical line have? Yeah, infinite. Don't tell me undefined anymore. Infinite, right? But what's different with this guy? Once again, technically f, we're looking at the derivative, but we're talking about f. Looking at f's derivative, f is not differentiable at x equals 0. But why this time? Because the limit as x goes to 0 up from below the derivative does not equal the limit as x goes to 0 from above the derivative, right? So from below 0, all the slopes are -1. From above 0, all the slopes are 1. So therefore, that doesn't work, not differentiable. So these non-differentiabilities are unique, are different from each other in that they're arrived at 2 very different ways. Vertical tangent lines, I have infinite slopes, infinite derivatives. Whereas sharp points, I have disagreeing. Now hold on, who could have been the original functions in this one? You shouldn't even have to think about integration, even though that's one way. Yeah, couldn't f have been the absolute value of x? What's the slope as I come in? -1. What's the slope as I go out? +1. Is there any converging to a set derivative or a set slope at the cusp, at the sharp point? It's not differentiable. And specifically, well, you guys, did you see down below, I actually graphed both of these, right? That could be the original function. Wait a minute, it's root of x, he's a basic graph. He's not that big a deal. Okay, whatever, like he curves, but you guys ever think about how he has a vertical tangent line at 0? Such a basic graph with an infinite slope, because this would keep on getting steeper and steeper and steeper as you make infinitesimally smaller steps towards 0. It goes higher and higher and higher and higher and higher, approaching infinity. We could also graph this guy, and this guy would have some sort of, maybe I should make the derivatives in the originals different colors. That would be smart. What color do you want to make the derivative graph? Blue? Sure. Why would that be the graph of the derivative? What's happening as the slopes approach 0? Infinitely high. What happens as the x goes to infinity? My slopes are getting smaller and smaller and smaller, right? So I have a vertical asymptote and a horizontal asymptote of this derivative function. But this guy, once again, a basic graph, such a basic graph. It's the D. The slope coming in is a -1. Going out is a positive one. Wait, why did I make them both empty? Why not do an or equal to somewhere? It doesn't exist at 0. Remember, if there is no agreement, the derivative defined to be a limit must agree from both sides. So yeah, no, the derivative does not exist, so I cannot include 0, and I would not graph include 0. See, we have two different ones. We have vertical tangent, the sharp point corner, and then the sharp point cusp. Okay, one more case, I forgot about it. I have this graph, but what's the function? What if I was to give you the absolute value of a quartic polynomial? Oh, no. There we go. Got it. How about x squared minus 4? Is he continuous? Yeah. Easy question. Why? No square roots, no denominators. No. What else? Imaginary numbers, that would be square roots. No logarithms, no trig. Yeah, he's continuous. Can I plug anything in? Anything. Doesn't matter. Any real number, he's fine. Continuous. Check. Is he differentiable? Nope. Where are the two places he's not differentiable? At positive and negative 2. So this function is not differentiable at x equals plus or minus 2. How do you know? How could we look at that though? Are you thinking, Lainey, of the function? Are we considering the function, or are we considering his derivative?
I'm thinking about what you did for the absolute value of x.
Okay. So what if we were to redefine, which the absolute value of x, I didn't actually give you the piecewise for the absolute value of x, except I know most of you guys know it's positive x and negative x, right? But how do we redefine this guy in terms of piecewise functions? Which, to be honest, was something that I wrote a lot lately. Oh, I'm in chapter 210. That's what I was writing. You guys will get those back tomorrow. I think they're already on my web if you want to look at them. But I said, I think on one particular problem, consider the piecewise. It's going to be very helpful for the entire group. So how do I rewrite this guy in terms of his piecewise values? Okay. What would the other piece be without even worrying about the interval? You guys see how the concept is the same? Keep it the same, make it opposite, right? Keep it the same, make it opposite, it being the argument of the absolute value. But what are my intervals? When does it stay the same? Tell me the idea. When does absolute value stay the same? When the values inside are... Oh, you know this. Absolute value, if you plug something in, when does it keep it the same? When you're plugging in and it is what kind of value? Positive. Good. So what would make this positive? Well, x squared better be greater than or equal to 4, right? So I could say, well, greater than or equal to... Oh, no. X squared greater than or equal to 4. So x has to be either... How about negative infinity to negative 2? But also 2 to infinity. Wouldn't it work for x outside negative 2, but also outside positive 2? Throw 3 in, he's fine. Throw negative 3 in, he's fine. Anything bigger than or equal to negative 2, sorry, more negative than negative 2 or more positive than positive 2. Are we good? So when does it flip? For all the little ones. For all the little ones. Throws me off. So if this is the original function, then question, what would his derivative be? In terms of piecewise, defined as a piecewise function?
So 2x.
Oh, yeah, it's easy. It's just 2x or negative 2x. If you know piecewise definitions, you don't even have to worry about that really nasty rule that we memorized last year, how to derive an absolute value of u. Does anybody think of that?
U over absolute.
Technically, it doesn't really matter to be totally honest. Oh, what did I forget? Right? That's an or. It looks like a log. There we go. So, without even having to do that, we could just write them as a piecewise and say, haha, 2x and negative 2x, but when? Well, wouldn't this be on the same interval? Except, why am I now all of a sudden going to change this and make everything open? Yeah. If I was to plug in a negative 2, which is a separator from this one to this one, that'd be negative 4, that'd be positive 4. They're disagreeing. If I were to plug in positive 2, positive 4, and negative 4, disagreeing again. So I still have disagreements. Another way of seeing it is that if you had done this with the actual definition, like the function definition, not the piecewise, this would be the exact same thing as the absolute value of x squared minus 4 all over x squared minus 4 times 2x. And if you went plugging in positive or negative 2, aren't they going to have 0 over zeros? And the way to keep going would have been to go make a piecewise definition. And a piecewise definition, sometimes this will be a positive one, and sometimes this will be a negative one. You could see the sign change that way as well. So you could technically see it in the algebraic form. Well, I guess they're both algebraic. But in the function form of the derivative or the piecewise form of the derivative. Either way, it's non-existent. And what do I mean by that? Well, you guys wonder how I built this function. I thought, what would be one where I would get some cusps? What would be one where I would get some cusps? And this one isn't a perfect cusp example, sadly. I thought I did get it, but until I found the actual derivative. What they technically mean by cusp, I believe, would actually be this function. Oh, I thought I found it, but I didn't. This is the one that they meant, where from one direction you're approaching a positive infinity, and from the other direction you're approaching a negative infinity. ln? Oh, ln of absolute value of x. No, that wouldn't have worked. Because then you would have the positive, and then you would also have the negative. Yeah, so that would work. Because you have your radical function, and then you have the reflection of your radical function. There you go. But that's one where it's not a vertical tangent line. It's disagreeing vertical tangent lines. So that's why this is a unique case, this one that they would call a cusp. It wasn't bad for us to look at the other one. It is curvature coming into a point, but they were specifically, I think when they're talking about cusp, we're talking about an infinite slope one direction and an infinite slope another direction, but opposite infinities. Still coming to what we've called before just a sharp point. It's like, well, it's sharp still. They disagree. The derivative is going to negative or going to positive infinities, but I need to throw an equals in there. There we go. So this would be one where the limit below so then f prime of 0, which is why the function is not differentiable, but any unique way from either of the other ones that we've seen. book's definition of a cusp. So we have corners, we have cusps, and we have VTLs, and all of that falls under the heading of differentiability, section 3.2. So if you guys want to go ahead and get section 3.2 homework written down, I think I have it. Not there. Here. Here. Homework number, not 8, I apologize, 7. Oh, it doesn't look that brutally long. It looks that brutally long, does it? And some of you have your books, but most of you don't. Some of you have taken pictures ahead of time. Most of you have not. So therefore, I'll throw up on my webcam. So you guys still have about 10 minutes. I think you can bust out some derivatives. Don't forget to write the original function, because it's making you slow down long enough to make sure you have all of the correct pieces. At the beginning of homework, you need what? 1, 9, 13 through 17? Let me freeze the screen for 1 second so you guys can be getting this assignment. While I get some of your first homework problems ready. I don't have the webcam open. That's not helpful. Okay, what are your first 3 problems? Sorry, 1 and 9? And then 13 to 17? Got it.
Dirty? That's nasty.
Yes, you may. Oh, I didn't want that. That's no fun.
But do you really not like a jet while just shooting down your eyeball?
Okay, let me do this instead. The picture-y thing is not working out well, but I think this will work a little bit better. Okay, here you go. Boop, boop.
So, are we allowed to take the derivative normally, or do we have to use the